So in the last lecture, we talked about the torque. In rotational motion, what is important is to consider the, could you please close the laptop, please? Yeah, thank you. Consider the torque, which is the rotating tendency of a force. So we saw that torque of a force is given by the distance r, which is the distance from where you want to take the torque to where the force is applied. So the application of the force, the location where it is applied is important. So the r multiplied by the perpendicular component perpendicular to r, the vector r. So this is what the torque is. So it depends not only on the force, it also depends on the distance from the pivot point to where the force is applied. So this is the magnitude, then it has direction. It's a vector. Clockwise direction, negative, counterclockwise direction, positive. So then we know the perpendicular component can be written as f sine theta, where theta is the angle between the vector r and the vector f. Then also we showed that we can alternatively give it like this. Not just the r, but the perpendicular r, the lever arm, or the perpendicular distance of the force to the pivot point, multiplied by f. Because it is the same as this, because r perpendicular is r sine theta and f. So we don't have two different results. It gives the same result, but different way of calculating it. So now we are ready to answer this question. When we have an equilibrium, it's a complete equilibrium. Not only we have the net force equal to 0, that's translational equilibrium, we also have no rotation at all. So the net torque is also equal to 0. So we got rotational equilibrium here as well as translational equilibrium. Rotational equilibrium will give, we can use this equation for rotational equilibrium. The net torque about any point. What is in equilibrium? The Planck. What is this? This is probably you have seen the children play. It is called the seesaw. Right? People sit in the opposite side of this bench-like thing. It is supported at the middle. Okay, supported here. So they sit either side. So they go up and down. It's a game. Okay, children's game. So here we have two people sitting either side of this seesaw. It is called seesaw. A woman is sitting, her mass is 55 kilogram. The man is sitting, his mass is 75 kilogram. So he is heavy. So if they sit the same distance on either side of the center, it is not going to be in equilibrium, right? Because this guy is heavy. Suppose he sat here, then it is going to, the balance will be, there will be no balance. It will rotate clockwise. So that's why he has to find a place closer to the center. He has to move towards the center, and he will sit at a certain place where the x is equal to some unknown thing. So when he sits at that place, everything is balanced in equilibrium. Our task is to find this x. The length of the Planck is given 4 meters, okay, because this is 2 meters, means the total length is 4 meters. So he comes closer. He doesn't sit at 2 meters from the center. He comes closer. We need to find what this value of x, so everything is in equilibrium. The way to find it is to apply the equilibrium condition, which is the net torque is equal to 0. Then we can follow and we get this. But we will do it in a next slide, in an empty slide. So we will start by saying, I'm going to apply this, the rotational equilibrium for this Planck. So the Planck is here. We need to show all the forces acting on this. It is in equilibrium. The woman's weight, small mg, acting there. And the man's weight, because he's pressing on this, so on the Planck, it will be down. capital mg, and he's sitting at a distance of x from the center of the support center. There are other forces. At the point where it is supported, there will be normal force, the wedge is pushing it up, and the gravitational force, the weight of the plank itself. The plank itself will have some weight. So let's say mass of the plank is mpl multiplied by g. That will be the weight of the plank. Okay, so now it is time to apply this equation. So we can apply this equation. We have to choose which point I am going to apply it on. If it is in equilibrium, I can apply at any point. So this point is called the point A, this point is called the point B, and where the man is sitting, the point C. Here, here, here. These are the 3 points that we can possibly apply this equation. But, we have to be a bit clever and figure out which point to choose. The best thing is to use the point B. You will understand why after some time when I go through the solution. Okay, but let me say, okay, I will apply it on the point P. This torque equation, you can apply at A. There is nothing against that. Any point, it can even be outside the plank. So if it is in equilibrium, the net torque must be 0 about any point that you want to take. But the best thing to do, take the point B. Why? We will know soon. Right. Net torque means torque from all the forces. How many forces we have? The weight of the woman, the normal force at the support, the weight of the plank itself at the center again, and the weight of the man. There are 4 forces. So we have to collect the torques due to all these 4 forces. Torque from the woman's weight, torque from the normal force, torque from the plank's weight, its own weight, and the torque from the man's weight. Add them and we will say equal to 0. I am going to take the torque about the point B. Right, let me start with this guy. So what is the torque? Torque will be, this is the woman right here. She's sitting here. So from the pivot point, you need to draw a line to where the force is applied. So the R will be this, and this will be the force. So you will say it is equal to the distance R will be 2 meters, and the woman's weight is, I remember, 55. So 55, that is kilogram. You need to multiply by 9.8 to make it Newton. Okay, the force is a weight. It will be 55 multiplied by 9.8. So you've got the, what about the sine theta? Because already it is perpendicular. The force is perpendicular to R. So sine theta is equal to 1. Sine 90 is 1. So it doesn't come. So you got the magnitude, but you have to pause here. Okay, do not be in a hurry. This is just the magnitude. Then we have to think about the sign, whether I'm going to put a positive sign or negative sign, because it has direction. It's a vector equation. Clockwise direction, which is into the board, counterclockwise direction, which is out of the board. Counterclockwise is positive, clockwise is negative. Now tell me which direction. This is the point, pivot point, right? We are taking the talk about the point B, and this is the force. If this is the only force and it is pulling, this woman is putting a force down here, which direction will it rotate? Clockwise. Clockwise is negative. Okay, clockwise is negative. Now the torque from the normal force. Can someone tell me quickly what is the answer for that? 0. Why? Yeah, the force is applied at B, and we have to get the distance from pivot point, which is also B, to where the force is applied. So we need the distance from B to B. No distance is 0. So that's why this becomes 0. So the torque from the normal force is 0. It is good for us because we don't know what the normal force is. What is given to us is this force and this force. Even this one, I don't know what is the mass of the plank is not given. So it is also okay for us because the torque from this is also 0, because that force is also applied at the point B, and I need the distance from B, the pivot point, to where the force is applied, that is also B, that is also 0. Oops. This is also 0, 0. So although I don't know what this is, I am saved, because I don't have to worry about their values, because I am taking the talk about the point B. Now you know the answer why I choose B. So I don't have to worry about not knowing the values of n and mass of the plank. Okay, so good. And what about this one? This is the force here, and you can see the R will be from B to C. Use another color. This is the R now, and this is the force. So again, it is perpendicular to R, so it will be, the distance will be x. We don't know what it is, right? That is what we want to find out. So let's call it x, and his mass is 75. So 75 multiplied by 9.8. Now tell me, do I put a positive sign or negative sign for this guy? This is the pivot point, and he is rotating. Is this correct? Is it clockwise? Now I'm going back to this first. This is positive, not negative. It is counterclockwise. This is the pivot point, and the woman will be turning like this. Is it clockwise? Counterclockwise. So this is positive. Okay. And what about this? About the point B. The man is trying to rotate it. Negative, clockwise. So this is negative. Equal to 0. Okay. So you see, you understand why this is 0 and this is 0. This is the torque from the normal force. This is the torque from the weight of the plank. So this is the torque from the woman's. And you must be wondering what happened to 9.8. There's a 9.8 here, right? And a 9.8 here. Because the rest of the terms are all 0, you can think we also have a 9.8 here, multiplied by 9.8, multiplied by 9.8, multiplied by 9.8. So you can say I'm cancelling because every term has the 9.8, which can be factored out. So they can be cancelled. So that's why you don't see the 9.8 here. So now it's a matter of just, very easy. 2 multiplied by 55. Okay. Minus can go to the other side, become positive. Multiply by 75. So that gives me x is equal to 55 multiplied by 2 divided by 75, which you get this answer. So we found very easily. You don't even have to do the translational equilibrium. This alone is enough to find what distance we should sit in order to bring it to equilibrium. Okay, right. Now, about this equilibrium, rotational equilibrium means angular acceleration is 0, not the angular velocity. Angular velocity doesn't have to be 0. Something can be rotating with a constant velocity, constant angular velocity. It is in equilibrium. The condition is angular acceleration is 0. So as long as it is rotating with the same angular velocity, it is in equilibrium. So it might look a bit strange, because when you say equilibrium, you think it has to be stationary. It's not like that. Okay, equilibrium means no acceleration. It can have a constant velocity. So remember that. Right. When you have a problem like this equilibrium question, these are the steps that you have to do. You have to read the question, of course, and if there is no picture in the question, you have to make your own diagram. So it is clear to you. Okay, it's always best to draw a picture, so diagram the system. And then this step is very, very important. You have to show all the forces in the correct place. Okay, so now it is no longer a point. Okay, it's an extended object. You have to show the forces with the correct direction and the correct position. Then you apply the equations. This is the rotational equilibrium equation. These are the translational equilibrium. It can be two-dimensional, but the rotational equation is only one equation, but you can apply it any given point, whatever point you choose. So you choose the point wisely. So you don't have any unknowns, only one unknown in the equation, so you can solve for that one unknown. It's like a one-dimensional equation. We have only two directions, a positive direction and a negative direction. All right, so these are more equilibrium questions. A typical question that might come in an exam. We have a ladder. Here is a ladder. You know what a ladder is? Okay, where you people climb, that is ladder, right? Okay, so there we have a ladder. It is supported on the floor and it is also supported on the wall. But this, it says, okay, the length of the ladder is given, the weight of the ladder is given, and it's it's leaning against the wall, which is smooth wall, no friction on the wall, but there is friction on the floor. If there is no friction, it will slip, right? It will always slip away from the wall, right? So, if you keep it like this, it's less likely to slip, right? If the angle is big, it will not slip. But as you make the angle smaller and smaller, maybe at one point, a certain angle, after that it will slip. He is saying at 50 degrees that angle, verge of slipping, meaning it is about to slip. If you make the angle less than 50 degrees, a little bit, it will slip. Okay, so that's the meaning of verge of slipping, right? So he has given that mean at this point it has got the maximum static friction force. So even make it a little bit more weight and it cannot make the angle less than 50 degrees, it will slip. Which direction will it slip? Obviously to the left. So what will be the direction of the friction force? Opposite. Friction force will always act so that it will stop the motion. The motion is to the left because of the slipping, so the friction force will be to the right. This is very important. Now you have to draw the force diagram. In the force diagram, you have to show all the forces in the correct direction at the correct place. And it is touching this, there will be a normal perpendicular force. Yes, so these two forces coming from the floor on the ladder. We are looking at the ladder, okay? What are the forces acting on the ladder? I am going to apply the equilibrium condition for the ladder. The ladder is not moving, that means it is in equilibrium. Constant velocity, which is 0, acceleration is 0. Then the ladder has a weight. So the weight will be acting in the middle, 50 Newton, the center of the ladder. And it is touching the wall. So there will be a normal force from the wall. So we call it P. There is no friction on the wall. So only the perpendicular force, the normal force, there is no parallel force. Now, one thing you need to understand, the label. For this normal force, I use the N. Usually we use N for the normal force. But can I use N for here also? Then you will get confused. Because if you label this as N, you're going to also give the same label for this, and you will think they are equal. Not really. They are not necessarily equal. So you better give a different label. So call it A, B, C, D, whatever you want. Here he is calling it P. P is the normal force from the wall on the ladder. So once you do this diagram, the force diagram, you are set. This is very important. Very, very important to draw the free body diagram in order to solve the question. Okay, so again, you can even show the angle if you want, like here, if it is given. Yeah, this angle is given. What else? Sometime maybe this D may be needed or may not be needed. The length is known, the angle is known. If you want this D, we can find that too. All right, we got this there. Then we can continue to solve this problem. So how do I solve this problem? Apply the equilibrium conditions. The net torque is equal to 0 and the net force is equal to 0. Let me start with the, oops. All right, well, I mean, this is not done, so I will also skip. There is no question here, but if there is a question, we can solve it. The next one we will solve. Okay, this one. This is another problem. This one we will solve. What we have here is a beam, maybe a concrete beam, and it is pinned to the wall. Okay, so pinned means it can rotate. So it is not nailed, it is pinned. So about this pin point, it can rotate. But anyway, we lock it, I mean, we stop it from rotating by attaching a cable here. So the tension will stop it from rotating. And it is kept horizontal with this cable here. The cable has a certain force. And there's a man standing somewhere on the beam. Right. Some angles are given, the length of the beam is given, so on. So first thing is to draw the free body diagram or the force diagram. So take the beam, we are looking at the beam. So the beam written separately. We cannot make it a point, okay? It's an extended object. The forces are applied in different places, so you have to draw the complete thing. Then draw the forces. So at this point where it is pinned, there will be friction force, there will be normal force with the pin and the beam. So there will be certain force coming from the wall on the beam. So I'm going to label it as R. That force is a combination of the friction and the contact force. They are all contact force, the friction force and the normal force. Let's say it is in some arbitrary direction. We can reduce it to one single force and let's call it R. We don't know what this angle is, but at least we know there is a force from the wall. At the point it is pivoted or pinned, and let us call this force as R. Then the tension force, we have been given this angle, so mark that angle as well, and that is called the T, tension on the cable. Then the beam has a weight, and in the question it is told to us it has a weight of 300 Newton. So at the center, this is the gravitational force or the weight of the beam, 300 Newton. And the man is standing there. It looks like he's heavier than the beam. So the man is pressing down on the beam and he has a weight of 600 Newton. Okay, we've got everything right now. From showed all the forces, whatever the numbers available, we put it there, the angle, the magnitude of the force, and so on. We don't know what this R is. We don't know what this tension is. And those are the questions. He is asking us to find R, the force applied on the beam from the wall, and find T, the tension that is supporting the beam from the cable. So these are the two questions. Okay, we can use the net torque equal to 0, also the net force equal to 0. This will be two equations if we consider the two dimension, x and y direction. The forces are in arbitrary direction, so we have to use both fx equal to 0 and fy equal to 0. So we do one thing here, further to this step. I'm going to choose my x direction horizontally to the right and y direction up. So let's look at the forces. This force is less troublesome. He is in the y direction. This force is in the y direction. But this guy is not in the x direction, not in the y direction. It is in between. So we better take the component. That will make it easy for us later when you apply the net force equal to 0. So that is what we are going to do. Now R, so I will say xy component is ry and the x component is rx, and we get rid of it. Okay, so the one force is replaced by two forces, one along the x-axis, one along the y-axis. And do we do the same thing? Oops. Yeah, we do the same thing for tension. So we get rid of this tension and replace it by two forces. One along the y-axis, the y component will be, because this angle is 53. Now we know the angle. Here we don't know. So we just leave it as ry and rx. But here, since I know this angle, I can say the y component of the tension is t sine 53, and the x component of the tension is t cosine 53, directed to the left. So that will help us greatly when I start solving the question. So let me go to the next slide. Let me start with the net torque equal to 0. And then I need to choose my point. What is my point x? We have several choices. I can choose it here. I can choose it there. I can choose it here. I can choose it here. Let me call it B, C, D. Any other point. If it is in equilibrium, net torque is equal to 0 any point. That is the condition. You cannot restrict to one particular point. It has to be 0 everywhere if it is in equilibrium. But we choose this point. Why? The same reason. I want to end up with an equation with just one unknown. I want to find the tension. So if I choose this point, I don't have to worry about ry and rx. The torque from rx and ry will be 0. So I have to only worry about, I don't have to worry about r, although we don't know that. We will end up with an equation with only the tension as the unknown. That's the reason I choose the point A. So here, net torque, so I mean torque from R, torque from the beam, the weight of the beam, torque from the weight of the man, torque from the tension in the cable, add them equal to 0, and I'm going to choose the point A to apply the equation. So this is 0. Done. Torque from the beam, the weight of the beam is here, right? So R will be, if I choose green, so this will be a R, the distance from the pivot point to where the force is applied, and it is equal to 2.5 meters. But anyway, at this point I will just write L/2. If the length is L for the beam, it is given as 5 meters. So 5 divided by 2 is 2.5, but let me just put it like that. Multiply by weight of the beam. Now what about the sign? Now you have to pause. This is only the magnitude. So this is the pivot point, and your force is here. Which direction it is trying to rotate it? Yeah, clockwise, minus. So that's why we put the minus. Now let me go to the next guy. Torque from the, we done that, right? Torque from the man's weight. The man is standing here, and his R will be this. How much is that? It is given to us at 1.5. And the man weight is, let me call it Wm. He is also negative. He is also negative. He is also trying to rotate it clockwise. Oops. Right. Now what? Tension. Right. So R will be, for this guy, the tension will be this. All the way from point A, where we want to take the torque, to where the force is applied. That will be L. Multiply by only the perpendicular component. Parallel component will have no effect in turning it. So that is why we said R multiplied by F perpendicular. In these cases, is already perpendicular. So the whole force. Why is a sine? Okay, that's the perpendicular component. In the question, it is like this, that the tension force is like this, and it is making an angle of 53. We want the y component, or the perpendicular component. So perpendicular component will be sine 53. So that's why, and it is plus. This is the pivot point, right? And this guy is up, so it is rotating it counterclockwise. Okay, so it's plus. Right. So we combine them, we get this equation. The only unknown in this equation is t. You just type it in the calculator or do the small algebra and calculate it, done. Now what about finding r? So we cannot use a, we can, if you want, you can do another net torque equation, but probably it's easier now. Just use the translational equilibrium. So find the Rx and Ry separately. So the net force in the x direction is 0. So in the x direction, Rx is positive to the right, and T cosine, the x component of the tension is to the left, T cosine phi to the negative, say it is equal to 0, then you solve for Rx, you will get this value. Then write this equation. In the y direction, net force is equal to 0, then Ry is positive, these two are negative, the weight of the beam, weight of the man, both are down, and the tension force is up, y component of the tension force, say equal to 0, then you solve for Ry, you will get the equation, done, finish. So we solve a question in equilibrium. Now we go to the dynamics of rotational motion, meaning applying the Newton's second law for rotation. How do we apply Newton's second law for rotation? You know what Newton's second law is, right? Net force equal to mass into acceleration. That is the Newton's second law. So when you go to the rotational motion, you now already know force is not what we have to look at. We have to look at torque. So net force become net torque. So the acceleration become angular acceleration, alpha. So we say, like we did with the Newton's second law, that is acceleration is proportional to the net force. Now the angular acceleration is proportional to the net torque, and it is inversely proportional to not mass. We have a corresponding quantity in rotation motion, which is called inertia, rotational inertia. Of course, you remember mass is called inertia because it is resisting the change in the motion. So this is the normal regular inertia. This is called the rotational inertia. Yeah, angular acceleration. A is regular linear acceleration, alpha is the angular acceleration, because we only have the rotating, the angle is changing. So angular acceleration is proportional to the net torque, inversely proportional to not mass. There is mass is the inertia, the linear inertia, but we have something corresponding quantity in rotation, which we call the moment of rotational inertia, or another name is moment of inertia. So we will now go there, but just I am introducing it now. So this becomes the Newton's second law for rotational motion. Now what do we mean by moment of inertia? This angular acceleration is proportional to the inversely proportional to an analogy of the mass in rotating system. That analogy is the rotational inertia. The symbol we use for that is I, capital I. You know, most of the time we call it moment of inertia, also rotation inertia. Both mean the same thing. It's your choice, okay? Sometime I will call it rotational inertia, sometime I will call it moment of inertia. Now, how do I define it? This is how we define it. It is not just the mass, it is mass into some r squared. Now, what do you mean by that? It's like, say, we have two masses, let's say m1 and another mass m2. Now, for this system of these two masses, if someone asks what is the moment of inertia for this system about a certain rotation axis, say this point O, say it is free to rotate about this, okay, and then you will say I is equal to m1 r1, this distance to that point where you want to take the moment of inertia, and this, the distance is r2, so it will be m1 r1 squared, m2 r2 squared. That's what it means. You know what this symbol means, right? Summation. We Greek letter sigma, the big sigma. This is big sigma, this is small sigma. So this summation, it means you're adding all the m1 r1 squared plus m2 r2 squared and so on with all the masses. Generally, you know, rigid object, okay, some continuous solid object, you know, you have to break it into so many pieces, small pieces. We call it m1 and m2 M3, M4, M5, and so on. You need to have billions of pieces. Okay, mathematically small, I mean infinitely many such pieces. Each one say M1, and someone can ask, okay, calculate the moment of inertia about this point O. Then you have to get this M1 R1, M2 R2, M3 R3, and collect all these M1 R1 squared plus M2 R2 squared plus M3 R3 squared, and so on. When you finish doing this calculation, that will be the moment of inertia. You must be thinking, how can someone do it, right? Yes, there are ways to do it, especially if the object is homogeneous and there is some symmetry. There are mathematical methods to calculate it, okay, calculus. But sometimes you don't even need calculus. Sometimes it is easy. We will see that. Right, now I am writing the Newton's second law again. Net torque is equal to inertia multiplied by angular acceleration, the rotational motion, Newton's second law. So you can see angular acceleration is directly proportional to the net torque. Angular acceleration is inversely proportional to the moment of inertia of the object. One thing you need to know when you apply this, the torque has to be taken around a certain point, right? And the I should be with the same point. They should match. If the point is A, inertia should also be above the point A. So they should match on both sides. Torque, when you say torque, it is about a certain rotation axis. So the moment of inertia is also it's going to be different depending on which one, which is the point of rotation. I can show you with a small example. Let's say you take a rod, like a scale or something, and you try to rotate it about the center, and you take the same rod and they try to rotate about the edge. Which one do you think is easy to do? In other words, if I apply the same torque for both, which one will have a bigger acceleration? First one. Because torque divided by I, right? This I for this guy is small, for this guy, it's the same rod. But when you're trying to rotate in the middle, I will be small. When you try to rotate at the edge, I will be big. Let me explain that. How come? Let me color this one, and the middle is color this one in blue, and color this one in red. So I can refer to them by the color. Half of it is blue, half of it is red. It's the same identical rods, right? If when you want to find the moment of inertia about this axis, you need to take this portion and get the M1 R1, M1 R1, M2 R2, M3 R3, and so on, right? So you can see the blue portion will have the same moment of inertia. The blue portion, when you calculate it, it will be similar to the blue portion you calculate here. So from the blue portion, you will have some value for the moment of inertia. We are not done with calculating. Then you have to get the red portion. If you look at the red portion, this guy will be similar to this guy. But this guy, when you want to calculate, it will be greater, because R is greater. So that means the right side thing has a greater moment of inertia. It's the same thing, but you are rotating about the point, the rotation axis is at the edge. So when the rotation axis is at the edge, that to do that rotation, it will have a greater resistance. So the moment of inertia, when it is about that axis, is greater. About the central axis, it will be smaller. Okay, right. So when you look at the moment of inertia and the mass, there's a big difference between them. What is the difference? Yes, moment of inertia depend on the quantity of matter, like the mass, but additionally, it also depends on the distribution of that matter in the body. So how it is distributed. If it is far from the rotation axis, it is going to have a more moment of inertia. So the moment of inertia depends upon the, also it depends on the location of the axis of rotation, because that will change how the mass is distributed about that particular axis of rotation. So now we have a very nice exercise to find the moment of inertia. We don't need calculus. We can do it very easily. For a ring or hoop, this is called a hoop. A thin hoop will be a ring. Okay, if the small radius, which you can fit it in your fingers, that's a ring. So something like a ring here, hoop. And someone asks you to find the I for this ring about the center axis. Some center, if someone, suppose you want to rotate it about the center, what will be the rotational inertia? So we are going to break it into pieces. I will call this piece number 1, M1, M2, M3, and so on. I'll go around it. So I will make it into small pieces. Okay, and I will take each piece. Let me take the first one, and I will get M1 multiplied by the distance to the center, R1. So I will multiply by R1. Can you see R1 is equal to R? The radius of the disk ring? Yeah. So M1 R square. The second guy, okay, then again I'll take the R2. That is also R. So I will say M2 R square. And the third one, same story. It goes on. And so on, so on, so on, until I finish with all the masses around this ring. Okay. Now I will say R is common. It can be factored out. In each term, we have the R squared. So R squared can be taken outside this. So when you take R squared from this, what remains? M1. When you take R squared from this, what remains? M2. And from this, M3. And so on. Can you identify what this is? M1 plus M2 plus M3 plus M4 plus total mass. So we are collecting all these pieces when adding it. So what do I have now? R squared into total mass. We have found. So we have now used our definition of the moment of inertia and figured out what is the moment of inertia for the ring about the central axis. It is equal to the total mass multiplied by radius squared. Right, now we can go on doing this for other homogeneous materials like hoop. It's again hoop, but it has got some height. So you can say it's a thin cylindrical shell. It is the same formula, whether it is a hoop or thin cylindrical shell, mr squared. This is a solid sphere. You know what is a sphere? Ball, right? Like a marble. What about football? Soccer ball. Is it a solid sphere? Yeah. It's a sphere, but is it solid? Come on. Pump air. Inside is hollow, cavity, right? So it is not a solid. You know what? That's the meaning of solid. Solid mean it is all the way in same material, okay? It's solid. Like a marble. Marble is a solid sphere. But football is not a solid sphere. It's a shell. So for that, about the central axis, this is the moment of inertia. And cylinder, solid, okay, all the way. Or you can call it disk. Even a pulley, which we come across in our physics problem, can be considered as a disk or a cylinder. So for that, it is half mr squared. The moment of inertia about the central axis is half mr squared. And this is for a shell, like a football. So it is not solid inside its cavity, hollow. So that's why it's shown like this. So for that, the moment of inertia about the central axis is 2/3 mr squared. Now you come here, which we discussed, a rod. So the rod shown differently. First, about the central axis, it is 1/12 ml squared. About an axis at the edge, it is 1/3 ml squared. So you can see again, which is calculated, which can be done, okay, with some integration because we say sum mr squared is the I, but when it's a continuous mass, we replace the sum by integration. So there are certain techniques to do this integration, which you will learn later. So by that, you can find the rotational inertia, the moment of inertia for a rod. The central axis is this, and on an edge axis is 1/3 ml squared. So it is greater. Around an axis at the edge, the moment of inertia is greater. Right. So this is the last slide in this. We finish with some application of the Newton's second law, simple application of a pulley, right? So we have a pulley. So let me draw it like that. And there is a string, a rope wound around it, and there it hanging, and there is a mass like the bucket of water. So it is hanging down. So there will be a tension force acting on this pulley. And there will be other force at the center. There will be normal force from the axle and the gravitational force, the weight of the pulley going down. Before, whenever we see a pulley, we neglect it. We say ignore, because we say it has no inertia, no mass at all. But we cannot do it anymore because we didn't know how to handle rotational motion. We ignored it. But now we are not going to ignore. So we can apply the Newton's second law for this rotating pulley. How? What is Newton's second law? The net torque is equal to I multiplied by angular acceleration. So again, as I told you before, so this guy is rotating above the center. We will take the net torque above the center, O, and then again, I also must be about the same point. That's very important. They have to match. So the net torque means torque from all the forces. We have how many forces? T, N, and mg. Luckily, N and mg will have zero torque because the point is O, and the force is also applied at O, the two forces, that will have zero torque. The only torque will come from T. And the distance of the T to where we want the torque is the radius. So R, T into R. This is the torque from the tension force. Is it positive or negative? Negative. It's trying to, the way I have drawn, it is trying to rotate clockwise. Equal to I0. No, pulley is a disk. So you go to the formula sheet, or it may be given in the formula, the question itself, half mr squared. I hope you remember it, okay, if needed. But it will be, most probably it will be given, half mr squared for the solid disk, the pulley, alpha. That's it. If you know the force, and we know the radius of the pulley and the mass of the pulley, one can calculate the angular acceleration. So just one simple application of the Newton's second law for rotational motion. Well, alpha will be negative. It is understood. If the torque is negative, the net torque is negative, alpha will also be clockwise, negative. Yeah, okay. Right. So that finishes our chapter.